Welcome to a lesson on inverse trig functions. In this video we will be looking at how we can determine the exact values of inverse trig functions at our special angles like 30, 45, and 60. And we'll also look at how we can approximate values of our inverse trig functions. We will look at some composition of trig and inverse trig functions. And then at the very end, we'll look at an application of a trig function. So just kind of like we did with normal trig functions, let's start out by defining them as ratios. So if we remember back to how we define our sine, cosine, and tangent, remember sine was the opposite over hypotenuse, cosine was the adjacent over hypotenuse, and tangent was the opposite over adjacent. And again, this came out of a right triangle, and we were dealing with an acute angle. So we can do the same thing, but for our inverse trig functions. And if you remember back to an algebra, your pre-calculus class, the difference between a function and its inverse, well, one of them was that we flipped the inputs and the outputs. So right now with our normal trig functions, the angle is the input and the ratio of the sides is the output. And so we're going to flip that. So we're going to define inverse sine. And sometimes you may hear it read or may say it as arc sine. This means the same thing as inverse sine. And notation, you could write arc, A-R-C, S-I-N. You could also write sin to the -1 power. So either of those would represent inverse sine. And notice that now the angle is on the outside and the ratio of the opposite and hypotenuse sides are on the inside. So we've flipped the inside and the outside, or the inputs and the outputs of our function. So the normal sine function, you gave it an angle and it told you what the opposite and hypotenuse was. The inverse says what's the opposite and hypotenuse, and it will tell you the angle. Okay, so similar for cosine. Normally cosine would take the angle and tell you the ratio of the sides, adjacent over hypotenuse. So arc cosine, or inverse cosine, is going to input, you're going to type in adjacent over hypotenuse, and the answer, the output, is going to be the angle. And again, same thing for arc tangent. So inverse tangent of the ratio of the opposite over the adjacent side will tell you what angle, what that angle has to be to give you that opposite and adjacent side. Okay, so it's just flipping around the inputs and the outputs for our trig function. So remember, with our inverse trig functions, we're putting in the sides, we're getting out the angle. So the answer to an inverse trig function, the answer is always going to be an angle. All right, and we can also define our inverse trig functions for arc cosecant, arc secant, and arc cotangent. We don't use them very often, but they are there if you ever needed them. But again, they're usually not programmed in on like a calculator or anything, so rarely would you ever have to use them. So let's look through some examples. So this first example here, we're given a right triangle with an acute angle theta. We have an opposite side of length 6 and then a hypotenuse of length 12. And we want to find the angle. So because we have the opposite and we have the hypotenuse, that deals with sine. So normally we would think sine is going to be the angle. So the sine of theta would be the opposite over the hypotenuse. Okay, so if we knew what the angle was, but we don't. So to find the angle, we're going to use our inverse. So the inverse of sine, we now are going to put the ratios of our opposite over our hypotenuse, and the answer is going to be theta. So we're trying to compute what is the inverse, sine inverse of 6 over 12. Okay, whatever that answer is, it has to equal theta. Well, 6 over 12 can actually be simplified a little bit, so we could get this inverse sine. 6/12 reduces down to a half. Okay, so what we're trying to compute at the end here is we want to find out what angle makes sine equal to a half. Okay, so that's the question we want to ask, is what angle makes sine equal 1/2. So if we look back at our unit circle, we know that an angle of 30 degrees will make sine equal to a half. So our answer here would be 30 degrees. Or if we wanted to write this in radians, we could say it would be pi/6. All right, let's look at another example. So again, we have an acute angle inside a right triangle. We have an adjacent side of 5√2, and we have a hypotenuse of 10. So because it's adjacent and hypotenuse, that would be dealing with cosine. Since we're trying to find the angle, we know that the inverse cosine of the adjacent over the hypotenuse must equal theta. Okay, and we can simplify 5√2 over 10. The 5 and the 10 will reduce a little bit, so we're going to have the inverse cosine of √2 over 2. That's equal to theta. And then let's pause and think, what does this mean? So what we're trying to think about here, the question we want to ask is what angle, because that's what we're trying to find, what angle makes cosine equal to √2 over 2. Okay, now, again, going back to the unit circle, and again, we're only dealing with acute angles right now. So what angle makes cosine √2 over 2 on the unit circle? We know that that angle theta has to be 45 degrees, or if you want to do it in radians, that would be pi/4. Now let's look at another one here. So we want to find again the exact value of our angle. Again, for the angle in our acute triangle, we know the adjacent side is 24, and we know the opposite is 24 over √3. So that's going to deal with tangent. So we know that theta must equal the inverse tangent of the opposite side, which is 24 √3, over the length of the adjacent side, which is 24. And again, the 24s will cancel out. So we know whatever the angle is, it has to equal the inverse tangent of the square root of 3. So again, our question, what angle makes tangent a square root of 3? Okay, and so tangent's a little harder. Usually the way I like to think of tangent, and remember tangent is sine over cosine. So remember tangent is sine over cosine. And in terms of units, in terms of unit circle numbers, if we think of √3 over 1, so just putting that denominator of 1, what numbers for sine do we have that deal with the square root of 3? Well, I know it's square root of 3 over 2. And similarly, the 1 would be a 1 over 2. Remember, √3 over 2 and 1 over 2, half, those are our unit circle values. So when is sine √3 over 2 and when is cosine a half? Well, that turns out to be the case when your angle, when theta is 60 degrees, or again, if we wanted to do that in radians, that would be pi/3. Our known. Now this time we want to look at approximate values of theta. So we're given our acute angle again. We have an opposite side of 9 and a hypotenuse of 13. So opposite and hypotenuse is sine. So theta is going to be the arc sine, or the inverse sine, of 9/13. So one thing we should observe here is that 9/13 is not one of our unit circle values. Okay, so since it's not unit circle, that means we're going to have to get an approximate value. That's why we're dealing with an approximate value here. So we're going to have to go to our calculator, and if we compute the inverse sine of 9/13, we will get an answer of, it's actually an approximation, of 43.81 degrees. Okay, now it's degrees because my calculator is in degree mode. Had my calculator been in radians, then this would have been in radians. Okay. All right, let's look at one more example. So again, we want to find an approximate value for our angle. It's an acute angle in a right triangle. We have an opposite side of 12 length and an adjacent side of length 17. So opposite and adjacent is tangent. So we know theta has to equal the inverse tangent of 12/17. Now again, 12/17 is not a unit circle answer, unit circle value, so we're going to have to use our calculator. And so we get that theta is approximately 35.22 degrees. Okay, so we've talked about our inverse trig functions as ratios, just like we did with our normal trig functions, but then we took a step forward and we talked about our trig functions as normal, as algebraic functions. So let's do sort of the same thing with our trig functions that we've now defined. Before we do that though, I kind of want to step back and review some of our properties of inverse trig functions, or just of inverse functions that you would have seen back in algebra. So I guess first we could think about notation. We could have f of x being a function. Its inverse is f with a little -1. It looks kind of like a -1 exponent, but it's notation. So f inverse of x. So what properties do we have? Okay, first is that any point that is on the original function, so if you had a point AB that was on the function, then its inverse has the same point where the coordinates are flipped. So if AB is on the function, then BA is on the inverse. Remember? We could talk about a function and its inverse being symmetric with respect to the line y equals x. So symmetric means they're mirror images of each other. So they are reflections across the diagonal y equals x line. If we thought about composition, so remember composition is taking one function and putting it into another function. If you were to take the inverse function and put it into, compose it with the original function, everything cancels out and you're just left with an x. And same thing with the reverse. If you put the function, composed it into the inverse, everything cancels out except for an x. And so both of those have to be true. All right, and then the last thing here is that the inverse is only a function if the original function is 1-to-1. So let's think about that sort of an idea here a little bit. We know what it means for something to be a function. So visually, right, something was a function if you could draw a vertical line test. So we had the vertical line test. So any vertical lines you drew could only hit the graph once. So all of these are only hitting at one time. Okay, so that represented it was a function. So if the inverse is a function, the same thing has to be true for the inverse. Okay, but remember that the inverse, if we go back to that second point, the inverse and the function are symmetric to each other. So if you flip things across that diagonal, not only does the inverse have to follow the vertical line test, But the function, the original function, has to be 1 to 1. And that means that if we take that same graph does it pass the horizontal line test? Okay, so we can think about the horizontal line test. So if every horizontal line touches the graph only once, then the function, the inverse, is a function. Okay, and that's again because it's reflecting it diagonally across that diagonal line. Horizontal lines become vertical lines, which makes the inverse a function. So if we're looking at the original function, those are kind of the two things we can look at to show that it is a function and that it is 1 to 1. Okay, so let's look at a more specific example that you would have been familiar with back in algebra. So let's look at just the function f of x equals x squared. So the first thing we want to look at is just to sketch its graph. We want to verify that it is a function, and then we want to see, is it 1 to 1? So let's start with that. So if we draw the graph of x squared, remember that was our parabola. So it's kind of like a big U. Okay, is that a function? If we do the vertical line test, right? Every vertical line here only hits the graph once. So it is a function. Is it 1 to 1? So 1 to 1 would be if we drew horizontal line test. So if we draw horizontal lines in here, how many times do these horizontal lines hit the graph? Well, sometimes none, but there are places where it hits it twice. So right now, it is not 1 to 1. Okay? And so this was something you should have talked about in algebra. How do we make it so that it is 1 to 1? And the answer to that is that we restrict its domain. So how much of this graph can we keep so that both vertical and horizontal lines will cross? So if we started at the origin, if we were to only keep the right half of the graph, so we basically get rid of the left half of the graph. If we keep from the origin to the right, it passes the vertical line test and it passes the horizontal line test. So that would be a 1 to 1 function. And we could keep the left and get rid of the right, but we'll just keep the right half here. So how do we make a function 1 to 1? We restrict its domain. So for this 1 to 1 graph, what is the domain? Well, my domain, it goes from 0 to infinity. So at infinity, we never have brackets. We always have parentheses. At 0, since I can actually include the dot, the point at x equals 0, 0 is part of my domain, and we can show that it's included with a bracket. Okay, what about the range? Now the range goes, those are the y values, that goes from 0 up to positive infinity. So it is also 0 to infinity. Now again, remember, the original function, the entire domain is negative infinity to positive infinity. So this one here is negative infinity to positive infinity, but when it gets restricted to make it 1 to 1, we get rid of the entire left half of the number line and we only start at 0. So algebraically, how do we determine the formula for the inverse function? So if you remember, that was where we would flip the x and the y coordinates and then solve for y. So we would say y is equal to x squared. We flip things, so we get x is equal to y squared. And if you solve for y, you have to take the square root. So y is equal to the square root of x. Technically, there's plus or minus here. But since we're keeping the positive values, we'll go with the positive square root of x. So this is that inverse formula. And we can do that as long as we can do the algebra. Okay, what is the domain and range of the inverse function? Well, a square root function starts at the 0 at the origin and goes up and to the right. So it has a domain from 0 to infinity, just as its range is also from 0 to infinity. Okay, because it goes all the way to the right and it goes all the way up. Now it so happens that both the domain and range are the same. They actually match the domain and range for the original function, y equals x squared. But remember, we talked about this, it flips the coordinates. So the domain for the function is actually representing the range for the inverse. And the range for the function is representing the domain of the function. They have that flipped relationship. All right, so could we sketch the function and its inverse on the same graph? Okay, so our parabola goes to the right and up. So this is x squared, and if we do the inverse, it goes up and to the right, so that's the square root. And again, if we looked at the line y equals x, that's that diagonal line. These two graphs should be mirror images of each other. So the original function is below the line and then it curves upwards. The inverse is above the line and then it curves below the line. Okay, so they're just mirror images of each other. And then the last thing is, what if we did our composition? So what if we first put the function into the inverse? Well, what's the square root of x squared? It's x. Well, what if we put the inverse into the original function? What's the square root of x squared? It's also x, right? So if we do both of these compositions, the end result is just x. So all of these are properties that they kind of review those properties that you would have seen in algebra, in pre-calculus. They're all properties that we have for inverse functions. So how do we take that and apply it to our trig functions? Well, I'm glad you asked. So let's think first about the graph for sine. Okay, so we know sine of x, the sine and the cosine graph are sort of a wave. And when we did sine graphs earlier, we did a wave that looked more like this. We started at 0 and we'd go to 2 pi, right? And so we had this wave. Well, that wave, again, is going to continue going on forever and ever. Okay, and it goes on in the negative direction too. It doesn't matter which way, it always is going to continue going. So our goal is, well, first, is that a function? Well, yeah, it would pass the vertical line test. Is it one-to-one? No, right? Because if you drew a horizontal line, it's going to hit it infinitely many times as it stretches off to the left and to the right. So just like we did with x squared, we have to restrict the domain to a smaller portion. And that's what I have on this graph here. This first graph shows the graph of y equals sine x. But centered at the origin. And I've highlighted in red, so two things. I've highlighted in red the part of the graph from negative pi over 2 to positive pi over 2, and then up and down from negative 1 to 1. So that red part of the graph is a function, because it passes the vertical line test, but that red part is also one-to-one. So if I drew horizontal lines through there, I would get a one-to-one function. It would pass the vertical and horizontal line test. Second thing I've also put in there is the diagonal y equals x line. Okay, so remember our properties. When you go from a function's graph to its inverse, it's visually going to reflect, it's going to be a mirror image across that y equals x line. And so this is, if we take that and we reflect it, we can get our inverse sine function. So notice a few things. We still have the y equals x diagonal line, but notice how where the original function was above or below, that's flipped for the inverse, right? So to the left of the origin, the sine of x was above the line. For the inverse sine of x, it's now below on the left side. Okay, and it's above on the right side. So it's flipped where it's above and below that diagonal line, because that's a reflection of the y equals x line. And then the second thing is notice how the inputs and outputs have changed. For sine x, we want to deal with pi over 2 and negative pi over 2 as x values. Well, the domain for the function becomes the range for the inverse. So pi over 2 and negative pi over 2 are actually the y values, the range for our inverse function. And then again, for the original function, the 1 and the negative 1, those were the range, those were the y coordinates. They have now become the x coordinates for our domain. They are the domain of our inverse trig function. Okay, so the whole thing flips across that diagonal line. It's a mirror image. So let's kind of summarize this, put it all into a definition. So when we think about finding an inverse sine or an arc sine, we are trying to compute the angle, and we've interpreted this before. We are trying to compute the angle whose sine is x. And sort of mathematically, we describe that as y equals the inverse sine of x. Okay, so we're trying to find y, that's the angle. We're trying to find the angle whose sine is x. Okay, it's kind of a flipped around kind of notation, the way we think about it, but it's reverse of what we were thinking about sine before. The domain now for your sine function is -1 to 1, and the range is from negative pi over 2 to positive pi over 2. Okay, we're not going to go on all the details, but we could follow the same restriction process as we did for cosine, but you can go back and just rewatch it for sine if you want. It's the same basic thing, just a little different. So when we define arc cosine as a function, we define arc cosine as the angle whose cosine is x. And again, our expression is y equals the inverse cosine of x, or y equals arc cosine of x. So x is the input for inverse cosine, but it is the output for the original cosine. Okay. So we're trying to find the angle with inverse cosine. And again, our domain is -1 to 1, just like it was for inverse cosine. A little difference though, our range for arc cosine is not negative pi over 2 to positive pi over 2, it is from 0 to pi. And again, that, just real quick, I guess, that comes from the way cosine, the original cosine graph works. Cosine kind of is that upward, upside down bell curve, so to speak, and we only need to keep half of it. If we keep here, everything to the left, so if we cut it at pi, everything to the left of pi, everything between 0 and pi passes the vertical line test, and it passes the horizontal line test, and I get everything from -1 on the bottom to +1 on the top. So that gives me all the y values, and it's 1 to 1 and a function. So I'm going to actually keep this part of the graph here. And that's what has been reflected for our cosine, inverse cosine graph. And again, we could do all this again for tangent. When we are computing inverse tangent, we are computing the angle whose tangent is x. Okay, so x is the ratio of your sides. Tangent's a little different. If you remember, again, with the tangent graph, when we drew them in a previous lesson, it was an increasing function. It passed through the origin, and it had the asymptotes at negative pi over 2 and positive pi over 2. So if we take that and we flip it sideways, we flip it diagonally across the y equals x line, remember the range, the domain here from negative pi over 2 to positive pi over 2 becomes the range, and then the range for the function from negative infinity up to a positive infinity, that becomes the domain of the inverse. Okay, so one of the nice things with inverse tangent is we can always compute inverse tangent. Inverse sine and cosine were only defined on specific intervals, so we have to be careful whether or not we can compute it or not. Okay, so let's look at some examples. We've already done a few of these, but let's try a few more here. So let's compute the inverse sine of √2/2. Okay, and again, the way we talked about this, when we are computing an arc sine or inverse sine, what are we computing? We are computing an angle. So we're trying to compute the angle whose sine is √2/2. Okay, and so what is that angle? In this case, it's going to be 45 degrees, or pi over 4. What about inverse sine of 2? So again, we're trying to compute an angle, and we want to find the angle whose sine is 2. Well, let's pause for a moment here and think. What is the domain for the inverse sine function? We just talked about this a minute ago. Domain for an inverse sine function is -1 to 1, because that's the range for the sine function. So is 2 in between -1 and 1? No, so it is not in the domain. So what angle makes sine equal to 2? None. Okay, so there is no solution. Or you could say this does not exist, which you can abbreviate DNE. If you try this on your calculator, it'll spit out probably some sort of domain error or something like that. All right, the third one here, what is the inverse cosine of 1? So again, that is asking, what is the angle that makes cosine equal to 1? Let's think about our domain first, just like we did in the last one. What is the domain for inverse cosine? Same thing as sine, -1 to 1, including the 1. So the 1 is part of the domain, so we can come up with an answer here. To figure out that answer, we just want to think about the unit circle. Where is cosine equal to 1? It's when it's on the positive x-axis, so that's the coordinate 1, 0 on the unit circle. So what angle makes cosine equal to 1? It would be a 0-degree angle, or a 0 radian. All right, let's just look at 3 more examples here real quick. What is the inverse cosine of a -√3/2? Okay, so we're kind of going beyond just the unit circle this time, or beyond the first quadrant of the unit circle. So again, the inverse cosine of a -√3/2, it has to be some angle, right? Some theta. What is the domain for cosine? It is from -1 to 1. Okay, now this one's a little different. It's negative. That is between -1 and 1, so we're good there. And you can compute that on a calculator if you want. What is our range? Well, for cosine, the range was from 0 to pi. Okay, so I need an answer between 0 and pi that makes cosine a -√3/2. So I know that cosine is √3/2 in the first quadrant. That's a positive √3/2. That is going to be at a 30-degree angle. So where is cosine negative? Well, it's negative in the second quadrant. So if that's a reference of 30 degrees, that's a reference angle, so that makes this angle 150 degrees. So it turns out that the inverse cosine of a -√3/2 is going to be 150 degrees, or that would be 5 pi over. So it's a little harder when we start dealing with these negative values, and I'll try to summarize this in a second. Let's look at inverse tangent of 1. So the inverse tangent of 1, again, I want to know what angle makes tangent equal to 1. So if we think through that on our unit circle, tangent is 1, and we'll just think in the first quadrant here. Tangent is 1 when both the x and the y coordinate are equal to each other, and that's at 45 degrees. So this has to be a 45-degree angle, or in radians, that would be pi over 4. And then lastly, when is inverse tangent, well, what is inverse tangent of a -√3? Well, again, we need to think of this in terms of the unit circle. We want to figure out the angle for an inverse tangent. So how do we figure out what the inverse tangent is? Well, there's several things we got to worry about here. First, how do you deal with the square root of 3? Again, I've kind of showed you that before, but I like to think of square root of 3 as a square root of 3 over 1, which I could then think of as root 3 over 2 divided by a 1 over 2. And this is the same because the 2's could cancel out and take you back. But I know that tangent is the same thing as sine over cosine. And what angle makes sine a root 3 over 2? That's a 60-degree angle. What angle makes cosine a half? Also a 60-degree angle. So in the end, I'm dealing with the tangent of a 60-degree angle. Okay. Now, where does tangent, what is the range for tangent? We know the domain for tangent was from negative infinity to infinity, so I can always compute this, but what was its range? Okay, if you need to, go back a few minutes and you can find that the range for inverse tangent was negative pi over 2 to positive pi over 2. Okay, so I have a 60-degree angle, which you could think of 60 degrees as a pi over 3. So I have a pi over 3 angle, which that would be if it's a positive root 3. So what changes if it's now a negative root 3? So a positive 60-degree angles is here in the first quadrant. A negative 60-degree angle is in the fourth quadrant. Okay, so this turns out to equal, so we're going to rotate negative down into the fourth quadrant. So we're going to have a negative pi over 3. Okay, again, this is kind of confusing, particularly when you're dealing with sine or with tangent, but let me try to kind of summarize some of this a little bit. When we're talking about inverse sine, okay, when we're trying to compute this angle, we know that the domain for inverse sine is from negative 1 to 1, and we know the range was from negative pi over 2 to positive pi over 2. So that means when I'm computing the inverse sine, my angle has to be between negative pi over 2 and positive pi over 2. Well, if you look at the unit circle, 0 is to the right, pi over 2 is the positive y-axis, and negative pi over 2 is the negative y-axis. So that means my answer, when I compute inverse sine, whatever angle I get, has to be something between negative pi over 2 and positive pi over 2. So my answer has to be somewhere on the right half of the unit circle. I'm not going to get an angle in the second or third quadrants. I'm also not going to get an angle in the fourth quadrant that rotated counterclockwise all the way into the fourth quadrant. It's going to rotate the shortest distance, which is clockwise, into the fourth quadrant. Okay, so you could also think of this as your answer being between 90 degrees and a negative 90 degrees. You're never going to get an inverse sine that produces an angle bigger than 90 or smaller than a negative 90. It's always going to be between these two values. Okay, it's on the right half of the unit circle. Well, what about inverse cosine? So when we compute inverse cosine, again, we are computing an angle. Well, we know the domain, again, for inverse cosine, just like sine, is negative 1 to 1. But the range changes a little different. The range is not from negative pi over 2 to positive pi over 2. We can actually do these as brackets because they can be included. For the range for inverse cosine, we said a minute ago, that was from 0 to pi. Okay, so 0 to pi, if we again look at our unit circle, we're starting here on the right side of the y-axis at 0. We hit pi over 2 on the y-axis, and then eventually we get to pi over here on the negative x-axis. Okay, that turns out to be the top half of the unit circle. And again, the reason it's the top half is because that includes all of the that includes the positive angles, or the positive x values, and the negative x values. Okay, so we have the positive x values, we have the negative x values. What are we doing when we do sine up here? We're doing the positive y and the negative y. So by doing just the right half of the circle, you get all the positive and negative y coordinates. By doing the left and the right, you get all the positive and negative x coordinates. Okay. All right, so the last one here is inverse tangent. Again, when you compute inverse tangent, you are computing an angle. We know the domain is negative infinity to positive infinity, so I can always compute inverse tangent. You're going to have to use a calculator, though, if it's not our nice numbers. What was the range? Well, the range was also, just like sine, was negative pi over 2 to positive pi over 2. But again, it's not including the endpoints, because that's where we got asymptotes when we looked at our graphs before. So it will be similar to what we saw with inverse sine, but we're not going to include the endpoints. So we're okay at 0. At the top we have pi over 2. At the bottom we have a negative pi over 2. And so it's everything in between. Okay. So when we compute inverse tangent, we're going to get an angle. That angle has to be either a positive angle in the first quadrant or a negative angle in the second quadrant. So it's rotating counterclockwise into the first quadrant or clockwise down into the fourth quadrant, and you will not get either of the endpoints. And again, for cosine, it's just all counterclockwise. For inverse sine, it could be a counterclockwise or a clockwise rotation. Okay, so this is kind of, it's really weird. It kind of feels weird to wrap your head around this, but it's something that we got to keep track of. Okay, it's already programmed to your calculators and stuff if you use a calculator, but we're not always going to have calculators to use them, so you need to know where these functions are defined and where your possible answers are going to be. Okay, so again, inverse sine is going to produce an answer in the first or fourth quadrants, either a positive or a negative angle. Inverse cosine is going to give you an angle in the first or second quadrant. And inverse tangent is going to give you an angle either positive in the first quadrant or negative in the fourth quadrant. The last thing we need to look at is a few properties that we have. So if we think about composing the functions and the inverses together, and that gives us, if you remember, we had to have things cancel down to x. So that will work some of the time. And so we have these inverse cancellation properties. And there's 6 total. We'll look at the first 3 here real quick. So if I were to take the sine function and put it into the inverse sine function, the sine and the inverse sine will cancel out. It's kind of like taking the square root of x squared, remember? So if I put sine into inverse sine, it will cancel out, and you're going to end up with whatever your input was. That will work if you're between negative pi over 2 and positive pi over 2. The reason it works there is because that's the range for inverse sine. Okay? What about cosine? If you put cosine into the inverse cosine, it will all cancel out, and you're left with just whatever your original input was. That only works if x is between 0 and pi. Well, that's the range for inverse cosine. Same thing for tangent, negative pi over 2 to positive pi over 2. The tangent and inverse tangent cancel. Again, that is the range for inverse tangent. All right, the other 3 options that we want to look at is if you put the inverse into the original function. So if you computed the sine of the inverse sine of x, that will cancel out and leave you just an x. If the x is between negative 1 and 1. Well, why does that work? Well, that's the range of the function sine x. It is the domain of inverse sine. So if you tried putting a number that was bigger than x or bigger than 1 in for x, like a 2, it would automatically be undefined because you can't compute the inverse sine of 2. Same thing with cosine. It will only cancel out if it's between negative 1 and 1. And the nice thing is if you compute the tangent of the inverse tangent of x, it will always cancel out and you're left with x. And again, that's because of the infinite domain, the infinite range of tangent and inverse tangent. All right, let's just look through 3 quick examples here. Suppose we wanted to compute the sine of the inverse sine of -2. Well, that would fit into the format of this 4th identity here, the sine of the inverse sine of x. Well, the cancellation only works if x is between -1 and +1, which 2 is not. But what do we know about the inverse sine of 2? We know this does not exist, right? Because 2 is not in the domain. All right, so automatically I know that this whole thing cannot exist either. So if part of it doesn't exist, the whole thing doesn't exist. All right, number 2, we have the sine of the inverse sine of 2/3. Well, this is going to fit into, again, the same, it's going to be that 4th identity, the sine of the inverse sine of a -1 of x will equal x if the x is between -1 and 1. Well, 2/3 is definitely between -1 and 1, right? So what is the sine of the inverse sine of 2/3 equal to? By our property, it is equal to x. So it is equal to 2/3. It's just like these two things just canceled out. Okay. All right, one more example. We have the inverse cosine of the cosine of pi/3. Which identity does that look like? That would be the second one that we listed up here, the inverse cosine of the cosine of x. So these cancel out if x is between 0 and pi. Well, how does pi/3 compare to 0 and pi? Is it between? Sure is, yeah. So in other words, this stuff all cancels out and you're left with just pi/3. All right, let's try a few more examples here. We want to do the inverse cosine of the cosine of 7 pi/6. So again, that's the same second identity we looked at just a second ago. Inverse cosine of cosine of x is equal to x if x is between 0 and pi. Well, 7 pi/6 is greater than 6 pi/6, and the reason I'm saying 6 pi/6 is because that's just pi. Okay, so this is not it is not between 0 and pi. Okay, so this does not work. Okay, which means the identity doesn't work. But does that mean we can't compute this? No, it just means the identity itself doesn't work. So we can compute something as long as we don't hit this does not exist wall. If we hit that does not exist, then we're done. But I can compute the cosine of 7 pi/6. Okay, to do that, think about the unit circle. Okay, so 7 pi/6 would be just past pi. Well, we know that the cosine of pi/6 is a √3/2. So since this is in the 3rd quadrant, we know that has to be negative. So I can compute this a little bit. We haven't done anything with the inverse cosine, but I know the cosine of 7 pi/6 is now a negative √3/2. And again, it's a √3/2 because this is a pi/6 angle, and it's negative because 7 pi/6 is in the 3rd quadrant. So the question then is, what is the inverse cosine of a negative pi/3? Well, we got to go back to the unit circle. When we compute inverse cosine, where would the answer possibly be? Okay, we just talked about this. The answer has to be somewhere in the 1st or the 2nd quadrant. Okay, since it's a negative, it's pointing over here into the 2nd quadrant. So I need to know what is the angle from 0 to something in the second quadrant that makes the x value a negative root 3 over 2? Well, it's got to be a pi over 6. What's the pi over 6 angle in the second quadrant? It is 5 pi over 6. So the inverse cosine of the cosine of 7 pi over 6 turns out to be 5 pi over 6. All right, what about the tangent of the inverse tangent of 9? Well, does that fit into an identity? So yes, it looks like identity, our sixth one. So the tangent of the inverse tangent of x will equal x if always, if x is between negative infinity and positive infinity. So in other words, because that 9 is a real number, again, tangent's a little nicer here, because we're dealing with tangent, inverse tangent, they just cancel out and we're left with 9. All right, last example here, and then we'll mix some things up a little bit. What if we're doing the inverse tangent of the tangent of 11 pi over 6? Well, what's our identity say? If we have the inverse tangent of the tangent of x, it will equal x if x is between negative and positive pi over 2. Well, 11 pi over 6 is not. Okay, 11 pi over 6 is going to be all the way around. It is in the fourth quadrant. Okay, it's a pi over 6 angle in the fourth quadrant. It is in the fourth quadrant, which, remember when we talked about inverse tangent, our inverse tangent has to be in the fourth quadrant or the first quadrant. But it has to rotate negative. It has to rotate in the clockwise direction into the fourth quadrant, which 11 pi over 6 is not. Okay, so to figure this out, we need to actually go through and do the computations. So what is the tangent of 11 pi over 6? So pi over 6 makes sine a half. Pi over 6 makes cosine a root 3 over 2. And because 11 pi over 6 is in the fourth quadrant, I know this has to be negative, which means I'm looking at right now the inverse tangent of a negative 1 over root 3. So what is the inverse tangent of a negative 1 over root 3? Well, again, I know it has to be an answer in the first or the fourth quadrant. Since it's negative, it has to be in the fourth quadrant. And we go back, it has to basically correspond to a 1/2 and a root 3 over 2 for sine and cosine, which corresponds to a pi over 6 angle. So it has to be the pi over 6 angle in the fourth quadrant rotating clockwise. Well, that just turns out to be a negative pi over 6. And here's the interesting thing. How is a negative pi over 6 related to an 11 pi over 6? If you remember the terminology, they are the same angle, just different direction of rotangle. They end at the same place. 11 pi over 6 and a negative pi over 6 are actually coterminal angles to each other. Okay, we had sort of the same thing happen, but not quite, in number 4 when we did the inverse cosine of the cosine of 7 pi over 6. Our answer went from a 7 pi over 6 to a 5 pi over 6. So it's still a pi over 6 angle. It just changed from the third to the second quadrant. All right, so let's mix our computations, okay? And let's think a little bit too about what we're trying to compute. So for this first example, we have the sine of the inverse cosine of a half. So what does this mean? I'm trying to compute, we want to find the sine of, so whenever you compute the sine of something, that something is an angle. So we want to find the sine of the angle. Okay, now inside we have this inverse cosine. Well, remember, what does inverse cosine represent? It means we're trying to compute an angle. So I'm trying to find the sine of the angle. Well, that angle has a cosine of half. So I'm trying to find the sine of the angle whose cosine is 1/2. Okay, And so we can just kind of, that's in sort of interpretation what we're looking at, and we can just kind of work through this from the inside out. So what angle makes cosine equal to a half? Well, a half is a nice first quadrant value, and we know that the angle that makes cosine equal to a half would be pi over 3. Okay, so what is the sine of pi over 3? Well, it turns out to be a root 3 over 2. Okay, so what is the sine of the angle who makes cosine a half? Well, the angle that makes cosine a half is pi over 3, and we know the sine of pi over 3 is a root 3 over 2. All right, the next one, we're trying to compute the sine of the inverse tangent of 1. That means we are trying to find the sine, and whenever you compute sine, it's the sine of an angle, so the sine of the angle. And remember, inverse tangent is computing an angle, so we want the sine of the angle whose tangent is 1. Okay, so just think about, what is the angle whose tangent is 1? Well, we know tangent is 1 when the x's and the y's are the same. When are the x's and the y's the same? Well, they're the same at a 45-degree angle. So that means we have a pi over 4 angle. So we're trying to find the sine of that pi over 4 angle. And we know the sine of pi over 4 is a root 2 over 2. All right, last example here, and then we'll look at an application. We want to do the inverse cosine of the tangent of pi over 4. Okay, it's a little harder to compute or to interpret what we're computing, but let's try. So when we compute inverse cosine, what are we computing? We're computing now an angle. So we want to find, and I'm reading from left to right, I want the cosine, the inverse cosine of the tangent of pi over 4. So we want to find the angle whose cosine equals the tangent of pi over 4. So we want to find the angle whose cosine equals the tangent of pi over 4. What is the tangent of pi over 4? It's 1. Okay, so that means I want to find the inverse cosine of 1. I want to find the angle that makes cosine equal to 1, because 1 is the tangent of pi over 4. So what angle makes cosine equal to 1? That's on the right side of the unit circle. The angle that makes cosine equal to 1 would be 0 radians, or even 0 degrees. All right, to wrap this up, let's just look at one application. The Willis Tower in Chicago is 1,451 feet high. We have a boat on the Chicago River that's 800 feet away, horizontally. What is the angle in degrees of elevation from the boat to the top of the Willis Tower? Okay, so let's first start with the picture. Again, this is a right triangle problem. We have a tower, and we know it is 1,451 feet tall. And we also have a boat sitting over here on the, you can draw it either way, but I drew it to the left. And I know that that distance is 800 feet. And I want to find the angle of elevation from the boat to the top of the tower. Okay, so we're trying to find theta here. And this shouldn't be too bad. We want to, given our acute angle theta, we're looking at the vertical side, which is opposite, with the horizontal side, which is adjacent. And so that's tangent. And so I know theta has to equal the inverse tangent of the opposite over the adjacent. So 1451 over 800. That doesn't really simplify, at least not in any of the nice numbers that we have, so we're going to have to use our calculator. And so we end up getting that our angle theta is roughly 61.13 degrees.